Hi everyone, welcome back. So in this video, I'm going to show you an analysis of a differential or subtractor amplifier. All right. So this is a circuit that we can use to amplify the difference between V1 and V2. Okay, or rather V2 minus V1. All right. So as usual, before we proceed with analyzing any circuit with an op-amp, just a reminder on the two assumptions that we are going to make. The first, of course, is that the currents into the terminals will be zero. So I1 and I2 will be zero because of we're assuming infinite input impedance on the inside the op-amp. The second one is that V1 will track V2 and V2 will track V1. So whatever V2 is, that's what V1 is going to be, or whatever V1 is, that's what V2 is going to be. So those are our two assumptions. So as usual, the first thing we do before we analyze any circuit is to label currents and voltages if it's not there yet. So first, let's just have a look at the current that is flowing through RF. So that would have been, so here I'm just calling it IF, all right? So they would have been like, that current would flow from VO through RF, and when it gets to this junction, because of the first assumption, there won't be any current flowing into the inverting terminal. So that means all of IF will end up across R1, sorry, through R1, right? So IF will just go through R1. So IF will go through RF and it will go through R1. So effectively, RF and R1 will be in series. Okay. Now let's have a look at this current. Let's say the current that is coming from V2. Now if I were to label that current as I2, so I2 would have gone through the resistor R2. All right, it would have gone through the resistor R2. But again, there will be no current flowing into the non-inverting terminal, which means all of I2 will then continue to go towards ground through RG. All right, so through RG. So I2 would flow from V2 to this node, and then all of it would then come down through RG. Okay, so now we have the currents, the voltages will of course be pointing in opposite directions, right? So we'll get to, okay, so let's just have a look at the voltage across RF. That's just that guy over there, right? That's the voltage across RF. It will be positive from the right node. It will be positive on the right node versus the left node. And similarly for R1, it will also be positive on the right side of R1. Okay. All right. Another thing I want to do is actually label this non-inverting node. So I'm going to call that VP, P for plus. All right. All right. So I'm going to put it there. And again, because of assumption number 2, if the non-inverting is a VP, then the inverting terminal would also be VP. All right. So they would be virtually at the same potential. Okay. All right, so you can actually solve this circuit in several ways. One of which is actually by using superposition theorem, where you have a circuit with multiple sources, yeah, V1 and V2. So you can solve this using superposition. But in this case, I'm going to solve it using KCL, KVL only. All right. Okay, so first you should notice that since I2 flows through R2 and RG, and that RG is actually grounded. So effectively, R2 and RG are in series, and V2 is the voltage across both of them. All right, and VP is the node in between the two resistors. So in other words, I can actually write a potential divider equation that links V2, VP, R2, and RG, right? So let's write that down first. So potential divider at VP, all right? All right, so that's basically going to be, so VP is going to be equal to V2 multiplied by RG divided by RG plus, oops, sorry, I need to put a bracket there, RG plus R2, right? So that's our standard potential divider equation, okay? So that's one equation. So VP equals V2 times RG divided by RG plus R2. That's the potential divider circuit that you see here. Remember, because there's no current going into the non-inverting terminal, hence we can write this equation. Now the other equation is the fact that we can say, well, we can write an equation for IF here, okay? Also that will have RF in it, and also an equation for IF here that has resistor R1 in it. All right, this was something that we've done in the past. So here I'm just going to write, I'm going to continue writing and say, okay, current through RF. All right, so that's going to be equal to IF, right? So IF is going to be equal to I equals V over R, so the voltage, remember, is pointing, so it's high potential on the right versus the left of RF. So I have to say VO minus VP, right? VO minus VP, all divided by RF. Okay, all divided by RF. All right. Another equation I can write about R1. R1, right, is again IF is equal to, okay, so here R1, the voltage across R1 is positive on the right hand side, so therefore we have to write as VP minus, sorry, VP minus V1, all right, all divided by R1. Okay, so that's our equation for the two IF, and of course they are going to be the same. So what I'm going to do now is I'm going to substitute VP, the expression for VP, into both of these equations, right? So first of all, I'm going to equate these two, right? So I'm going to say equating the two equations, the two IF equations. Equating two IF equations through RF and R1. And R1. All right. So therefore, we're going to have an expression that is like the following. So we're going to have this term here. So we're going to have this term here. All right. Equal to this term here, right? So that's what we're going to have, that one. So I'm going to copy this. Copy. That is going to be equal to this. All right. Okay. Then what we do is we then substitute the expression for VP, which is here, into our equation. So substituting VP into the equation above. So what we're going to get is, so let me just copy this whole thing first. Okay. And then replace every occurrence of VP with that expression. So this is going to be a bit small. All right, so that's that one, and then this is the VP here. Okay. All right, so next I'm going to put RF across to the other side. So the idea is I want to isolate VO on one side. So VO equals something to the right. All right, so I'm going to put RF across the other side, which means that which means that the left side would be this expression at the top here. All right, so that's what's going to be on the left side, equal to, well, it's going to be this RF multiply here means I'm going to get RF over R1, so RF over R1 multiply by all of these, this whole thing here, right? Multiply by all of this up here. All right. Okay, so close that. All right, I know it looks a bit of a mess. So what I want to do next is I want to move this minus V2 times all of this term over to the right-hand side. All right, so let me just copy the whole thing and paste it. Okay, so now this side becomes, so this won't be here anymore. So this won't be there. All right, so it's going to be plus those terms just now, the one that came from the left. All right, so it's going to be equal to that. Okay, so let me just multiply them out. Okay, let me just multiply them out so that I get a. So the idea is I want to collect V2 together. I want to join V2 together. All right. So that's the idea. So I'm just going to copy this. Okay. And put it here. So the difference is, okay, so I'm going to multiply it out. So I'm going to get this term multiplied by that term. So that's going to be one part of it. All right. Okay, so I'm just, maybe I need to take this out. And then there is a minus. Okay, I'm going to put that minus, you know, this RF over R1 times negative V1 here. I'm going to put that at the back. All right, so I'm going to put that at the back. So minus. All right, minus is going to be minus. It will be this term here multiplied by V1. All right, I'm just multiplying this bracket out. All right, so that's what I have now. So now I can combine V2 together. Well, so that means I'm going to take V2 out. Well, actually, I can take. What can I take? Well, actually, I can take V2 times all of this term out. Well, not out. Factor these two parts, right? So I'm gonna just copy that. Go to the end. Okay, so let me just. So in other words, I'm going to have this term here going to appear as a factor. So all this is going to, that is going to be this. All right. So you won't have that anymore. All right. So I'm going to have that expression. So in other words, I'm taking this term here, V2 times RG over RG plus R2 out as a common term. Then what's left is an RF over R1 plus 1, right? This whole thing just becomes 1. And then minus the item, the thing at the back there. Okay, so this part looks kind of familiar. It's like, you know, RF over R1 looks like the gain for an inverting amplifier, whereas 1 plus RF over R1 is the gain for a non-inverting amplifier. All right. So I'm going to leave this like this. All right. Now let's have a look at one particular scenario. Okay, let's look at one particular scenario where what happens if, RG here is equal to RF, and then R2 is equal to R1. So if you look at this, if I make RG equals to RF and R2 equals to R1, what will happen to this expression? Okay, I'm running out of space here. Let me just put this at the top as a continuation to, yeah, like that. All right, so I can continue with this. All right, so now, so let's make that assumption. So let me write that assumption first. Okay, so if Rg is equal to Rf and R2 is equal to R1, all right, so what will I get? Well, so let me just write that out in terms of what it would look like. Okay, so let me just copy this and put it down here. Okay. Okay, so what's going to happen? Well, I said that Rg becomes Rf, so fine. So that's going to be, so this part is going to be Rf, right? And so that's also going to be Rf, correct? And R2 becomes R1, so fine, this becomes R1. Now, this term here, Rf over R1 plus 1, now if I were to, you know, make it a common make R1 a common denominator between these two terms. So what I'll get at the top will be Rf plus R1, sorry, plus R1. All right. The reason I'm doing this is you'll notice that we can actually cancel certain terms out. All right, and then everything becomes over R1. So the idea is this whole center part will just become this. All right. So nothing changes at the back there. So, but now you notice that, well, Rf plus R1 will cancel out with this Rf plus R1, right? So let's highlight that to mean that we're canceling them. All right, so we can cancel those terms. All right, so then what you're left with is, well, you have a V2. So let's continue here. So you have a V2. So equals to, well, you're going to have V2. But then multiply by, well, what's left inside the bracket will be Rf over R1, right? Rf over R1. And then minus, well, virtually the same, I mean, basically the R1 part, which is this. Which you can again further simplify because now there are common terms. So I can put Rf over R1 outside. And then in brackets, I can say it's V2 minus V1. And there you have the final expression for the differential or subtractor amplifier, where V out is equal to Rf over R1 times V2 minus V1. All right, so that's going to be the final expression for VO. All right. So clearly you can see here that Rf over R1 becomes a gain, a differential gain, if you like, right, that multiplies the difference between V2 minus V1. Okay, and again, if you make Rf and R1 the same, in other words, if you make all resistors the same, then what's going to happen is, of course, you get VO equals V2 minus V1, which is exactly what a differential or subtractor amplifier is supposed to do. All right, so that's how you analyze it. So thanks for watching. I'll see you guys in the next video.